Okay, so we're going to do a few examples of finding confidence intervals for unknown population means mu, where we know the standard deviation sigma of the population. So just as a reminder, the C% confidence interval goes from x bar minus z star sigma over root n to x bar plus z star sigma over root n. And z star is known as the C% critical value. It represents the point on the standard normal curve, or the z-score, that captures the middle C% of our area. So the empirical rule says that if C is 95, right, then z star would be 2, because we get 95% of our area within 2 standard deviations of the mean. That's a fact that we're going to use in the first example that's already worked out in the notes, but I'll go through it here. Known standard deviation, sample size of 100, we want a 95% confidence interval. We're trying to estimate the unknown population mean IQ, mu. So we take a simple random sample of size 100, we get 98 as our sample mean, and we want to say precisely what that tells us about the unknown population mean mu. And our language for doing so is to produce a confidence interval, a 95% confidence interval. So for 95% confidence, using the empirical rule, z star is about 2. It's 1.96 exactly, or more exactly, but we'll use 2 here. So the margin of error for our confidence interval is 2 times 15 over the square root of 100. So that's 2 times 15 over 10. That ends up being 3. Well, if 3 is the margin of error, then the confidence interval is 98 plus or minus 3, which means we go from 95 to 101. And the interpretation of this interval is really important. So you'll be asked to do this on the exam, on the final. It's a really important piece of the work that we'll be doing. So this interval means that we are 95% sure the true unknown mean IQ of our population is between 95 and 101. Right? So we're pretty confident about the result. But there's still a fair amount of wiggle room in that interval, right? The mean IQ could be anywhere between 95 and 101. Right? Well, as is always the case in stats, we have to live with some of that uncertainty, right? Because we're sampling a population, we can't ask everybody in the population. All right, now example 2 keeps everything the same. Sample size of 100, sigma is 15, x bar is 98, but now it wants a 99.7% confidence interval. In other words, we want to be almost 100% sure that our confidence interval includes the true unknown mean. We were 95% sure here, and that's pretty sure, but 99.7% sure is really, really sure. Right? So that changes the z star. Right? The empirical rule says that z star will be 3, because the empirical rule says that we get 99.7% of our area within plus or minus 3 standard deviations of the mean. So that changes our margin of error. The margin of error is now 3 times sigma over root n. And so the margin of error is 4.5 now, and our confidence interval is now 98 plus or minus 4.5. So that's 93.5 to 102.5. So it's important to notice that what happened to our confidence interval is the price we pay for wanting to be more sure that we really got the true mean in there. Right? We're now 99.7% confident, but we had to relax the interval. In other words, we had to expand it. Now we're 99.7% confident, but we're only that sure that the mean is between 93.5 and 102.5. So we're more sure, but it's a less precise estimate. Right? We were 95% sure we were between 95 and 101. If we want to be almost 100% sure, then we have to expand our tolerance for error. We expand the margin of error. All right. The next example, we do one from scratch with one of the points that the empirical rule doesn't cover. So we want a 97% confidence interval for the true unknown mean weight of shelter dogs based on a sample of size 36, where the sample mean for those 36 dogs came out to be 27 pounds. So first thing we need is the Z-star for 97% confidence. And that you have to get from StatCrunch. We'll go through that together in a separate brief video. So there's my Z-star. It makes sense that it's a little bit bigger than 2 because 2 gets 95%, so a little bit bigger gets 97%. And 2.17 is the number. That makes our margin of error equal to 2.17 times sigma, which is 12, over square root of the sample size, which is 36. And I'll use a calculator to help with that. So that's a 12 there. So 12 over root 36 we can do, that's 12 over 6 or 2. So 2 times 2.17, the margin of error is 4.34. And so I need 27 minus that. That's about 22.7. And 27 plus the margin of error gives me about 31.3. Okay, so that's our confidence interval for the unknown mean weight of all shelter dogs. And the way we interpret it, which is again really important to be able to do, you'll have to do it on the exam and the final, we are 97% sure that the true unknown mean weight of shelter dogs is between 22.7 and 31.3 pounds. Right? So, the margin of error, we're within plus or minus 4.5, roughly 4.5 pounds. We'd probably like to do a little bit better. And the next example sort of shows us how to plan a study if we know ahead of time how close we want our result to be. So that last one, example 5 in the notes, tells us we want to be within half a pound of the true mean weight. So that is another way of saying the margin of error in this study has to be 0.5. We're also told that our confidence level is 95%. Let me just double check that. Yeah. So the Z-star is actually 1.96. You could use 2 also, but I'll use 1.96. And then I'm multiplying by the sigma of 12. And then the last thing that we don't know is the sample size, right? That's what we're trying to figure out. So again, the setup is we want to be 95% sure that we're within a half pound of the true unknown mean weight. So how many dogs have to be in the sample to make that happen? Well, that's a little bit of an algebra problem. We could cross multiply. That would give me 0.5 root n is equal to 1.96 times 12. So root n, if I move the 0.5 over, let's see, what do I get? 1.96 times 12 divided by 0.5 is 47.04. And so to find n, I have to square that, square both sides. And when I do, I discovered that if I insist on being 95% confident that I'm within a half pound of the true mean weight, the price we pay is we have to sample about 2,213 dogs. So can't sample 0.7 dogs, so we would round up, and we would have to conduct a really large study. But that's because the restrictions we imposed on ourselves at the beginning. We want to be really close and really sure. Well, then you have to get a lot of information. You have to sample a lot of dogs. Right? So those are a few representative examples of the sort of thing that we'll be doing with confidence intervals when you know sigma. Later on, in a couple of days, we'll talk about what happens when you don't know sigma. And next up, we'll do a couple of examples with sample proportions.